Intermediate Algebra Section 2.1. We're going to graph some equations, and to graph an equation means to make a drawing that represents all of its solutions. To do that, in this section, initially, we're going to just simply pick some values for this equation and find the ordered pairs. And to do that, I have a table here. You may recognize this equation. It is a linear equation, and if you know the relationships in this equation, it can do some shortcuts by all means, but when all else fails, when you're asked to make a drawing of an equation representing all of the solutions, one method is to do the following by picking a variable value, plugging it into the equation to find the other value, and then graphing the resulting ordered pair. So here are my headings. I'm going to pick some x values. To make it easy, we'll start with 0. We'll replace x with that value. Following order of operations, we multiply first, which results in 0 plus 3, gives us a y equal to 3. Summarizing that, we have an x of 0 and a y of 3, so that point is part of our graph and is a solution to the equation. Remember that what we look at a graph are points that satisfy the equation, whatever that equation may be. Continuing on, if we let y equal 1, multiplying again first, following order of operations, we get a negative 2 plus 3 gives us 1, and summarizing that value, if we let x equal 2, replacing x with 2 in the equation, we multiply to give us a negative 4, a negative times a positive. Negative 4 plus 3 results in negative 1. And let's take a look at what the graph of this equation results in. All good graphs should have a scale. I'm going to go by ones on the coordinate system I have here. Horizontally, our x-axis, and vertically we'll have this, our y-axis. The first point we found was 0, 3, which means no displacement in the x, and 3 in the y. Next we had 1, 1, and then we had 2, negative 1. We have a trend going here, and if we connect these points, we have the graph of a line, and I'm putting arrows on the end to indicate that this is continuing off in opposite direction, and recognizing that any point on this line, I've only graphed 3 points, but between these 2 points is another point. If we could determine the coordinates of that point, we would find it satisfies this equation or is a solution to the equation. Between those 2 points, I could find another. Between those 2 points, another, and so on. Every one of these, provided we can find the coordinates of the point, tell us that it is a solution to this equation. In this next example, we're given the following equation, and we'll use the same procedure. Further in this course, we will work with this particular type of equation and get a better sense of the characteristics of an equation that has a second degree power to it. So right now, though, we'll set up our table, plugging in some values so that we can find some solutions to this equation, and then make a drawing representing that. So a good place to start is 0. To find what y is, we'll replace x with the value chosen, which is 0. Following order of operations, we'll square or take the exponent first. 0 squared is 0 plus 3 is 3. And summarizing that, here is one of our solutions, the ordered pair 0, 3. Let's let x equal 1. 1 squared is 1 plus 3 is 4. So we have the point 1, 4 as a solution that makes this equation true. If y If x is a 2, what will y be? We have 2 squared is 4, plus 3 is going to give us 7. So we have the 0.27. We can see a trend here as our x is getting larger. Our y will follow right along. Let's try some negative values. -1 for an x. Quantity squared, a negative times a negative is a positive. So we have a 1 plus 3 is going to give us 4. So we have -1, 4. And we'll go with one more here. -2 in place of x. When squared is 4. 4 plus 3 is going to give us 7. So we have the -2, 7 as coordinates of another solution to this equation that makes it true. Plotting these points, again, we'll use the horizontal axis as x, vertical as y, going by a scale of 1 in both directions. Seems like that will be a fit for our points that we need to graph. 0, 3 is landing on the y-axis with no displacement in the x. Up 3, we had a point of 1, 4. Our third point was a displacement 2 in the x and 2, 4, 6, 7 in the y. Then we had -1, positive 4, and then we had -2 and a positive 7. 2, 4, 6, 7. If we use a smooth curve to connect these solutions, we have an upward opening curve. We will find, again, further in this course, this is called a parabola with certain characteristics with it. But recognizing we only found 5 values here, just like with the line that we graphed in the last example, between any 2 points we can find another. If we can determine the x and the y, that would be a value that satisfies this equation, as does any point, which there is an infinite number on this graph. Looking at another example, they're asking us to graph this equation, which you may not recognize, but our technique of plugging in some values to find solutions seems to be working. It may be a little time-consuming, and for graph or equations that we graph quite frequently, we do develop some shortcuts, but when all else fails, we can certainly set up a table and generate a list of solutions like we're doing here in this beginning of our graphing chapter. Some values, starting with 0. Absolute value is the distance this point is from the origin. It will always be positive since we're talking about distance with absolute value. And you can think about absolute value like grouping symbols. It has the priority. So we take the absolute value of 0, which is 0, minus 3 results in -3. So one solution to this equation is the ordered pair 0, -3. If we replace x with 1, the absolute value of 1 is 1, always positive, minus 3 is a -2. So we have the point 1, -2. Do another positive value here. Absolute value of 2 is 2. 2 minus 3 is -1. These values are getting smaller, so let's go one more positive x value. Absolute value of 3 is 3. 3 minus 3 is 0. So we have some solutions there. Let's try some negative x values. The absolute value of -1 is 1. Minus 3 is -2. And -2. We have room for one more point here. The absolute value -2 is 2. 2 minus 3 is -1. So let's plot these points. Again, horizontally we'll call that the x, and vertically we'll call that the y-axis. Going with a scale of 1, 1 to plot our points. The first one 0 out in the x direction, but -3 in the y. we had 1, -2. The next point was 2, -1. And the next point was 3, 0. So 3 in the x with none in the y. We seem to have a trend. If we continued with positive x, it's reasonable to believe that this would continue off in this direction. And we could verify that with some more test values. Then we had our negative x value that we plugged in. We ended up with the point of -1, -2, and a -2, -1. So it seems as though if we continued on with smaller and smaller x's that our y's would increase and that we would have a trend going off in this direction. There are the points here, 1, 2, 3, 4, 5, 6 that we actually found, but one more time just to illustrate that between any 2 points is another point, and between those is another and another and another. This line represents an infinite number of solutions that if we could read off the coordinates of the point, they would satisfy the equation. You will have some problems also in this section that ask you to determine whether a point is a solution to the equation. So, for example, if you are given y is equal to 2x plus 4, and they ask you whether -1, 2 is a solution. What they're giving you is an ordered pair xy, and if we could see the drawing of this equation, is this point part of that equation? Well, we could graph this equation similar to what we just did and see whether the point -1, 2 is part of it, or perhaps the easier method is to test whether when x is a -1 and y is a 2, whether it gives us a true statement, whether it satisfies this equation. So in place of y, we will put 2, and we're testing to see whether 2 times the x, which is given, of a -1 plus 4 results in a true statement. Well, there's nothing to do on the left, but on the right, we'll multiply. We get a -2 plus the 4, and simplifying, we end up with a -2 plus 4 gives us 2. So in this case, since we have a true statement, we would say yes, that this is a solution to the equation. If they gave us another ordered pair, -3, 3, and the question was still, is this a solution to the given equation, we'll similarly test it. Our y value is the second value, that would be 3, replacing it in the equation. Does it result in the same value on the right side when we replace x with a -3 plus 4? Well, nothing to simplify on the left, but on the right we'll multiply. A negative times a positive, and 2 times 3 leaves us with a -6 plus 4. Adding those together, we end up with a -2 is not equal to 3. So if we could see a graph of this equation, -3, 3 would not be part of the drawing or the graph, and therefore it is not a solution to the equation.